Hi everybody, welcome to this video. In this video, we're going to be going over a derivation for the Lab 3 of ECE 2245. Before we get started, my name is Shamna Keller, and since it's the zeitgeist of the times to show your dogs and whatnot, this is my sweet little puppy, and he'll be my moral support while I film this video. But anyways, without any further ado, let's go ahead and get started. So I'll just share my screen real quick and we'll work through this derivation together. Another quick note I'd like to point out is that the real purpose of this derivation is to help you work through it if you get hung up. And I would really appreciate it if all of the students or any people who are using this video in the future try to work through this lab derivation on their own. And, I'll tell you to pause the video at key points to try and give it a shot on your own. It's really worth doing that. You'll not only learn more, but you'll get more out of this exercise than if you just skip to the end and use the answer. So again, please try to watch the video and work through it on your own. But yeah, in this lab, we're going to be designing a bandpass circuit. And the bandpass circuit is going to pass the frequencies 3 kilohertz, and it's going to reject the frequencies 1 kilohertz. So you can read through the introduction to get an idea of why we might use a bandpass filter. In short, basically this is really useful for all sorts of radios and communication systems. If I have like a filter at a given frequency, I can pass through frequencies such as like 98.1 megahertz maybe. That's like a radio station. And the filter, a bandpass filter, might look something like this, where if this is the transfer function, we're going to pass through frequencies at our target frequency and around. And so the sharper that your filter is, the better it's going to work. And ideally, we would try to get a filter that passes within maybe 1/10 of a megahertz if you're designing a radio, but that's going to change based on your application. Okay, so I'm going to just highlight a few things as I go through this. The circuit will strongly reject one frequency, 1 kilohertz, and it will strongly pass another frequency, 3 kilohertz. This is the circuit topology that we're going to use right here in figure 1. And the input to this is going to be a triangle wave. But if we wanted to, we could actually send in a specific frequency and test the output at that frequency as well. The reason why we're using a triangle wave is because of Fourier analysis. I don't think we've really covered that in class right now, but a quick sort of intuition as to why we want to use this is because a triangle wave is actually composed of a number of different frequencies. It's not just one frequency. So by using a triangle wave, we can actually see the output of multiple frequencies at once. Here it talks about the transfer function. And basically what it's telling us to do is find the transfer function for everything to the right of these two nodes. So I'm just going to kind of highlight it. And essentially what we're doing here is we're finding the transfer function of this circuit. We have R1, and then we have our filter. Oh, it's a strange one note sort of tool that just happened. So this filter ZAB, that's the impedance to everything from the nodes A to B. So we're going to essentially model C1, C2, L, And this is the resistance of the inductor, so I'll actually just label it R sub L in this derivation. But everything to the right of those nodes we'll just model as some sort of impedance, ZAB. And so then we can go ahead and find the transfer function of this circuit. And that's really easy to derive, but let's just do it real quick because I can see that, if this is V out from the voltage across this impedance V out, I would write that V out, if this is V in is this voltage source, V out will be equal to V in times, we want the impedance that I'm using for my voltage divider divided by the sum of the total impedance. So that's R1. And then therefore H is just equal to V out over V in. And I can see if I compute that I get ZAB over ZAB plus R1 as my transfer function. Yeah. Okay, so to achieve the behavior of this band filter centered at 1 kilohertz with an impedance of L and C2 is designed to be 0 at 1 kilohertz. So really what this is saying is, in order to get this desired behavior, we can impose constraints on our bandpass filter. And these are the two constraints we're going to impose. And so I'm actually going to write those out right here. I'm going to say we have that ZAB is going to be equal to 0 at F1, which is equal to 1 kilohertz. And our second constraint, ZAB, is going to be equal to some infinite value at F2, which is equal to 3 kilohertz. So with these two constraints, we can go ahead and actually start to derive how this circuit's going to behave just based on what we see for the circuit topology up here. And I gotta make a quick pause of this recording. One moment. Okay, so I believe we're back recording. Now, well, let me double check because I don't want to waste a bunch of time. Cool. Yeah, we're good. So now that we have our two constraints, and I'm just going to label them as equations 1 and 2. This is essentially all we need to find the rest of these circuit components. And so let's start with constraint 1. So I'm going to actually make a little bit more room over here. So constraint 1. We want to say that ZAB is equal to 0. That's going to be accomplished by shorting out this C2 plus L. We're going to ignore R sub L here because of two reasons. Reason 1 is that R sub L is ideally the inductance of a wire, or the inductance of, the resistance of the inductor, which is also the resistance of a wire. It should be minimally small. And reason 2, it's not frequency dependent. So one sec, if I expand out, add some room over here. So that is to say that ZC2 plus ZL will be equal to 0. And so if we have that scenario, we're going to have ZAB looking something like this. If this is node A and node B, we just have a capacitor and a zero resistance sort of short right there. So that's what we've done. Okay. Now let's just fill in this math here. So ZC2, that's going to be 1 over J omega C2. And you'll actually want to leave this as J omega, not S, because we're going to use this equation to really quickly find what our C2 values are. Okay. And oops, sorry. We also have to add in plus J omega L. And so all of this is equal to 0. So doing some quick math, I can see that I have a negative J here, because 1 over J is equal to negative J. So if that's a negative J on this term, then I can just add that over and get J omega L is equal to plus J over omega C2. And now I have a J on both sides, so I can divide J on both sides. So that gets rid of the J. And then I can multiply my omega over to get omega squared. And I'll divide by L. So finally, I arrive that omega squared is equal to 1 over L C2. That's wonderful. Okay. Or, you know, conversely, if I want to solve for C2, I could also say that C2 is equal to 1 over L omega squared. Now we can actually pick this up and run, because we know that based on the lab packet, if you continue through here, it tells you what values to use for your inductor. And, you know, off the top of my head, you could probably use a lot of different, like, I think relatively any inductor value would work. But it says here, using L equals 100 millihenries, calculate the values of C1 and C2. So we can do that right now. Let's go ahead and use L equals 100 millihenries. And here we want to use omega equals 2 pi f. And f for this, remember, for constraint 1, ZAB equals 0 at 1 kilohertz. So we'll use f equals 1000. Okay. So plugging those in, we get that C2 is equal to 1 over, I'm going to do 100 times 10 to the negative 3. And then here I'll do 2 pi times 1000 squared. And let me just quickly plug this into my calculator and make sure I get the correct value for C2. So let's see. We have 1 over 100 milli times 2 pi times 1000 squared. Yeah, and we get 2.533 times 10 to the negative 7 farads. And I can see if I move this over 1, 2, that would be -8, -9. So this is equal to 253 nanofarads. And that's, you know, since we won't find that value in the stockroom, we'll just use 250 nanofarads approximately. And that should be enough, or that should be close enough. Get a pretty tight band on our filter. Okay, so we found C2. Now, we can use this value. I think it's worth also leaving it symbolic in our derivation. And so I'm going to write 1 over L 4 pi squared and then F1 squared. So that's what I'll use for C2 in the rest of this derivation. It's definitely worth, not plugging in numbers, because if we put in this function, it will kind of tell us how the circuit behaves. So let's go ahead and work out constraint number 2. So constraint number 2 says ZAB is equal to infinity at 3 kilohertz. So constraint 2, ZAB equals infinity. And what is that going to be? So, and also this is at F2. Okay. So looking at the circuit, this is a point when it's great to pause the video and think about how we could calculate what ZAB is, just right off the top of my head. So pause it and maybe come up with an answer for how you'd calculate ZAB. And assuming you've done that, what I see is, if this is ZAB, I see C1 in parallel with C2 plus L. Okay. Now, we can just write that as ZC1 in parallel with ZC2 plus ZL. Okay. So let's go ahead and compute that. Now, what I see when I compute this is here I can use just the parallel resistor sort of function, which might look something like this. Except for instead of R1 and R2, I would use these different things here. So I'm going to erase this and write out kind of how I see it is this is going to be ZC1 times ZC2 plus ZL divided by ZC1 plus ZC2 plus ZL. Okay. Now, for a moment, maybe stop taking notes and just write how I kind of think about doing this. This is a generalized approach, but we're going to do something even slicker for this problem. But for now, I'm just going to show you a quick way to work out this nasty impedance fraction in your head, like on the fly. So ZC1, I can fill that out as 1 over SC1. ZC2 is 1 over S times C2 plus ZL, which is SL. And if I do that in my head, I'm going to get 1 plus SLC2 divided by, and in the denominator, I'll just have SC2. Now, I could do that sort of approach in my head again, and it might even be worth doing. But sometimes it's better to just write it out as it is, because it's really easy to make mistakes when you're doing that with 3 different fractions. But so now that I have it written out, I can see that I would get the identical thing where it would be a C1 here, a C2 there, an S squared L C1 C2. And then our denominator should contain all those terms. So it's going to be C1 plus C2 plus S squared L C1 C2 divided by S C1 C2. Okay, so the reason why I showed you this was just to show you that you can do these sort of impedance adding really quickly once you get sort of accustomed to this approach of adding fractions. And it's definitely a skill that will come up again in this class. And this is nice because now I can see that my denominators cancel and I can get some easy to use function that would be, really quick to use. But remember earlier I mentioned there's a better method for this because we know that this is equal to infinity, right? Well, what if instead of adding everything together and coming up with this complex term, I can just realize that, I'm setting this equal to infinity, so that's kind of like setting it equal to 1 over 0. And in doing this, I immediately realize that the denominator of my function is going to be 0. So really, I'm just setting all of this equal to 0. And that's a super convenient trick. So let's just go with it. So if I have ZC1 is 1 over SC1 plus 1 over SC2 plus SL equals 0. And working with that, yeah, it's probably best now to add them all up. So then I would get that's equal to this fraction I ended up with over here. So that's C1 plus C2 plus S squared L C1 C2 divided by S C1 C2. Now I can see that if I multiply the denominator over to the right-hand side, I can start solving for some terms, and that denominator will vanish. So I'm left with 0 is equal to, and continuing with our previous theme, this is like setting it equal to 0 over 1. So I can see that it's just my numerator that's 0 now. So that's C1 plus C2 plus S squared. That's J omega squared L C1 C2. And, oh, sorry, this should be J squared. I know that J squared is -1. So maybe I'll pen that in. And I can see that if I just add that over to the other side, I get this expression that C1 plus C2 is equal to omega squared L C1 C2. All right, now previously I had solved for C2, so now we should just solve for C1. Ooh, maybe I should have left it all on the same side. I think I'm gonna do that. So before I isolate anything, I should solve for C or isolate C1. So if I pull a C1 out of these two terms, then I would get I'd get C2 plus I'll have a C1 times 1 minus omega squared C2 and an L. I'm going to rearrange those. So it's L times C2. Let's make sure I did that right. So yeah, 1 minus omega squared L C2, all times C1. Okay, yeah, so now I can find C1. So if I subtract C2 over and divide by 1 minus omega squared L C2. And let's make sure that I did that right. Looks like I have a sign error that I'm just gonna really quick go find. Yeah, just a moment. Sorry about that. There's actually no sign error. It's just that my derivation notes looked a little different. But a better way to write this is if we factor out a -1 on the top and bottom, then we'll just get C2, and that's omega squared LC2 minus 1 in the denominator. So this is equal to ZAB at F2. And the reason why that's kind of necessary is because, of course, we can't have a negative capacitance. Now, that's actually debatable because a negative capacitor is sometimes referred to as an inductor. And the reason why ties back into, like 1 over J omega C is also equal to negative J over omega C. But if we can, we could potentially set that equal to some inductance value. And that's why it's sometimes said that a negative capacitor is an inductor. So maybe we could actually use an inductor for this C2 value as well. But anyways, regardless, I'm going to move on with the derivation, and we're nearly finished. So we got our ZA value at F2, and it's right here. It's worth mentioning that we could plug in C1 real quick just to see what the frequency dependence is. So this omega, remember, that's at F2. So that's going to be 4 pi squared F2 squared. That's omega squared right there. And then we still have L and C2 minus 1. And remember, previously we had actually solved for C2. So what was it? 1 over L 4 pi squared F1 squared. So let's just put that in. So that's 1 over L 4 pi squared F1 squared. And in the denominator, we're going to have 4 pi squared F2 squared L divided by C2 is L 4 pi squared F1 squared. So that's C2, and then we still have the minus 1. And I can see that a bunch of stuff cancels here. My 4 pi squareds cancel, and my L's cancel. And this final very intuitive, or this equation that gives us a lot of intuition. I'm going to move out this entire numerator. So that's just out front. And then my denominator was OneNote's kind of hard to get enough room with OneNote. But then I would just have F2 squared over F1 squared minus 1 in the denominator. And I can actually see that F1 squared also cancels out, which I didn't realize before. But let's go ahead and write out over 4 pi squared L times 1 over F2 squared minus 1. And that kind of looks like a cube, so I'm going to just clean it up. But yeah, so this is our equation for ZAB at F2. And it's nice to see this because, yeah, you could plug in F2 would be equal to 3,000 squared. And this would be 1 over 4 pi squared times 10%. So that's like something like, I don't know, maybe 1 over maybe that's 1/5 times 1 over about 3,000 squared. So yeah, that's essentially I don't know. This is kind of oh, this wasn't ZAB, that's why. This should be what I solved for here wasn't ZAB. This was actually supposed to be C1. Anyway, so sometimes the reason why I went through this exercise of solving and writing out all these values to get C1 in a form that's easier to see is because it gives us some intuition as to what C1 is and what sort of things would affect it. And it makes sense that it's only going to depend on F2 squared. Okay, so that's going to give us our C1 value. We can actually plug it in using this step right here. So C2 was 250 nanofarads. Omega squared here, that's going to be 2 pi, and F is actually 3,000 squared times 250 nanofarad minus 1. When I plug this into my calculator, I get 2.8 nanofarads. Let me quickly just verify that this is the right answer before I end this recording. Always good to double check your work. I just had a typo and that typo is, one sec, right here. I need my inductance value in my equation, and we can see that right here. So just once again, to be super clear, I was solving for C1 using this equation. And I got 32 nanofarads when I did that. So this is actually equal to 32 nanofarads. Okay, so we found C1 and C2. So 250 nanofarads for C2. C1 is 32 nanofarads. And that gives us everything we need for the circuit. Now, remember, we didn't find the resistance of our inductor. That's something that we'll actually measure. RL, this is ideally 0. And if you wanted to, you could add this resistor value into our derivation. And that might give you a simulated or like a MATLAB value that's closer to the actual measured values. But regardless, I'm willing to bet that what we solved for here will still give us a first order approximation that's pretty good. So yeah, we have solved the derivation for this circuit. Moving forward, the rest of this lab is pretty straightforward. You will go and actually build this circuit and measure it. And you'll also make a MATLAB plot of this. So it tells you right here, characterizations of components. Of course, always measure and write down the actual values for your resistor. Do the same for your inductor. And yeah, just to be clear, we want a 10 kilo ohm resistor for R1. And when you purchase your capacitors, make sure to measure those too using an LCR meter. Okay, motivation. Yeah, this is kind of the big idea with this lab is that we can actually predict the output of the filter circuit. And in doing this, you want to write a MATLAB program to calculate the filter output. So if you wanted to, you could actually write these equations for C1 and C2 directly into MATLAB. And then all you'd have to do if you wanted to design this filter circuit again for different frequencies, all you would have to do is plug in different frequency values, and you would end up computing all of this. And so that's pretty nice because in the future, designing a filter can be done in just a few steps. Just open the MATLAB script and change your frequency values. So that's super cool. And yeah, so moving on with this section 7, plots of the filter response. Basically, as the first step in calculating the output of the filter, write a function that calculates the transfer function. So you will just write code that computes the transfer function versus frequency, and go and plot that. So it'll look something like this, Oops. You'll plot h omega as a function of omega. And maybe it looks like they use this one. So yeah. I think that pretty much sums up this lab. That I don't really need to say anything more. A quick side note, you're probably wondering, like, why this circuit? How did somebody come up with this circuit as a filter? What I see is a capacitor in parallel with an RLC circuit. The answer to that question, it can be really complicated, but you'll learn more about this in electromagnetics and particularly in microwave engineering, that basically you can a sort of generalized approach to filter design is by using something called a T circuit, which looks like this. So all these boxes are impedances. So you can use a T circuit, or you can use a pi circuit, which is essentially the same thing. So a pi circuit looks like this. I think this middle line goes through. Yeah, definitely. Oh, maybe not. I'm not sure. But yeah, so a pi circuit looks something like this, and you can see that this sort of looks like the symbol pi, and this sort of looks like a T. So pi and T circuits is a more generalized approach to circuit design. You'll learn about this in microwave engineering, and it's sort of like the theory that undermines how you would come up with this individual circuit. And it's not immediately obvious, but I believe this is actually, I believe this is a pi circuit in disguise, but we can have that discussion more maybe in class or something. So anyways, I hope this video was useful, and I'll see you in lab later. Thank you.